Hello, hello. Can we hear? Good morning, good or good afternoon, good afternoon. Oh, good afternoon. Hello, hello. Good afternoon, Sanam. Thank you. And wait, I just realized. Okay, hold on. Hello. That was Sonam. Hello. Bear with me a second. I just realized that I made a mistake on something, as you may have noticed. Right. Okay. I know people are here. Give me a second. Sorry. Just okay. Okay. Where are we? Oh, good afternoon. Yes, thank you. Okay, here we go. Now people are saying, okay. So the chat. Yes. Good afternoon, Sonam. Like I said, good afternoon, Roger, who was here very early. I appreciate it. Good afternoon, Sydney. Good afternoon, Genesis. Good afternoon, Ariana. Good afternoon, Kaya. Good afternoon, Matthew. Good afternoon, Gabriella. Good afternoon, Duran. Thank you for the prof shout out. Okay. So good afternoon, everyone. Good to see you. Um, love Alfred's avatar, although love is kind of a strong word, actually. I'm intrigued by it. Okay, good to see you all. We finally have a week with two classes in the same week. That's great. Okay, so I want to get back to physics, obviously. We're going to start moving on in the material today to two-dimensional motion. That is, I'm going to start. I want to start practicing the fundamental concept that underlies lab number three, lab number four. I mean, I know you've already turned in things. I mean, anyway, what you were doing in lab number three and lab number four is you were entering the world of two dimensions. You were starting to apply physics in a plane rather than in a line of space, right? And similarly, homework seven, which we have to get to, um, is all about putting together our physics ideas and applying them to two dimensions at once. So that's what we're going to start getting to today. I'm not going to bang through a million homework problems today. I'm going to give you one fundamental method, technique, operation that underlies all the material. Like I said, lab three, lab four, and homework seven. And then we'll keep going with more details and specifics in future classes. However, before I get, oh, thank you. He says, all right, awesome. Thank you. And happy Halloween, if that's anyway. However, before I get to this two-dimensional stuff, um, which gets us into angles and trigonometry and things like that, before I get into this two-dimensional physics of today, let me clear the air about something or announce. Of course, as many of you have notice, it is starting to get close to time for an exam. We do have to have an exam in this class. Nobody likes taking exams. I don't like, I mean, they're not any more fun for me than they are for you, et cetera, et cetera. But it is a reality. Um, so hello, Karen. Good to see you. So I want to say a couple of things about our upcoming midterm exam, and I will say a lot of things about it as we get in subsequent classes. But first of all, the way this class works is we have a midterm exam and we have a final exam. We have one midterm exam and we have one final exam, and they are not small pieces of your responsibility to the class. You may have noticed that just now, like 3 seconds before class, I posted an announcement in Google Classroom just to outline some facts and expectations and um, chronological facts about your midterm exam, which now is going to start to be a focus for us. Um, the midterm exam, Well, both exams in this class, but let's talk about it. The midterm exam is a take-home exam. I have a lot to say about that. I'm going to try not to say too much today, but it is indeed a take-home exam. That's sort of good news and bad news. Well, it doesn't matter whether you view that as good or bad. It's the fact. So first of all, what I just posted in Google Classroom is that um, a week from tomorrow, that is Thursday, the 31st of October, is when the actual exam will be posted no later than 8 p.m. on Thursday, October 31st. It may be a little earlier, maybe like 7:30, but no later than 8 p.m. Your exam will be posted. And then you have all weekend to do it. You turn it in, you submit it through Google Classroom by class time, by 12:15 p.m. on Monday, November 4th. Okay, so first of all, now again, there's lots more details to say about it, but first, just so you can plan your schedule, your expectations, or whatever, I'm saying the exam will be posted Thursday. You have all weekend to do it. I apologize that Thursday is Halloween. I didn't do that I mean, that is a bummer. I actually like Halloween too. But even if you take Halloween super seriously, I'm just saying the exam will be posted. It doesn't mean you have to do anything with it that night. Whatever. You have all of Friday, all of Saturday, and all of Sunday to work on this exam and then turn it in no later than the beginning of class on Monday, the 4th. Now, again, there's more to say about it in terms of format and substance and all this. But before I go any further, first of all, can you just raise your hand, electronic hand, if you see the posting in Google Classroom that I'm referring to? Like, is it there? Is it visible on your side? Okay, great, awesome. Okay. And I know there's a lot of words. Okay, great, terrific. Thank you. Awesome. So, and I know I get a little bit swept up when it comes to exams. Like, look, I find exams stressful, just like you do. I do. And I'm going to warn you right now that no matter how hard I try, I'll end up saying a bunch of things about it that are in the effort to reduce your stress. But I know from experience that the more I talk about it and the more I sound the way I sound, sometimes it increases people's stress. That is not my goal. I'm not trying to make this more of a stressful experience. Um, so I want to be careful, but so we're not spending this whole period talking about it. I assure you of that. Um, we will say more about it in the next class and the next class and stuff like that. And of course, you're welcome to reach out to me by text or email, and make a Zoom appointment or an office hour appointment or whatever, if you have specific questions. But the first thing I just want to say right now, the first thing to make clear is it's a take-home experience. Oh, and sorry, Alfred, is that a question or is your hand still up from the other thing? Because I'm happy to answer questions right now if it is a question, or no, maybe not. Okay. Um, thank you. Okay, awesome. Um, so the first thing I just want to make clear right now is chronologically, like, yes, it will be posted in a week and a day from now, as I think hopefully the Google Classroom thing says. And it'll be due back right before class on the following Monday. So the first thing before we go any further, I know that's sort of soon, look, nothing is perfect, and all of you always have a million things that you have to do, and a million things are in conflict. Like, of course, there's no time that's going to be perfectly dedicated only to physics. But my impression is that if it is posted a week from tomorrow and then due back the following Monday, my impression is there isn't one huge thing that affect it. My impression is that doesn't directly conflict with orgo, for example, which is usually my concern. Like, so I guess what I'm saying before we go any further, is it clear to you and manageable? Can you confirm with an electronic hand? Can you confirm with electronic hand that you understand and can accept basically the idea that the exam will be posted October 31st and due back at thank you. Due back on November 4th, 12:15 p.m. Awesome. Thank you, Ariana. Thank you, Joran. I appreciate it. Thank you, Genesis. Thank you, Sydney. Thank you, Matthew. Thank you, Samantha. Thank you. All right. Awesome. Thank you, Roger. All right. So, okay. So thank you. All right. You could tell it. Look, believe me, anyway, whatever. I feel for you. It's not easy being a forensic science student. I know. To, and I have speeches about that. Believe me, I've got all kinds of pep talks and preachy sermons ready to go for you when you're feeling bereft in this major. But this is not the time. Okay. I'm going to say a little bit more about the exam now, a little bit more. I'm going to say a little bit like every day, okay? But I'm going to say a little bit now. And again, this is meant to give you perspective and clarify your expectations. It's about the exam. As far as like what it will cover or how it will look or what's the format, well, the good news is there is a practice exam that's already posted in Google Classroom. It's been sitting there since the beginning of the semester. That I would recommend that there's an exam. It's the midterm from last semester or from 2 semesters ago or something like that. That is there on purpose as a practice exam for you. You don't turn it in. You don't get a grade on it, anything like that. It's 100% practice. So you can get a sneak peek, like so that you can know in advance exactly what I mean by exam or what you're expecting, what your exam is going to look like. Your actual exam will look very, very similar. It will be based on the last year exam that's already posted there. Like in other words, you're not cheating if you look at a past exam, not at all. I'm giving it to you to make that clear. Your actual exam will be very similar to the thing that's already posted in Google Classroom. It will definitely not be longer. It will not contain any material that you don't see in the practice. It may contain some less. But the practice is the most possible that you could be responsible for, the greatest number of questions or the greatest different topics or whatever that you could be responsible for on your actual exam. So really, I am saying that if you started like tonight or whatever, practicing that practice exam, like doing it and you felt comfortable with it and you could do the whole thing, and you could do the whole thing accurately and stuff like that and felt very confident, you would have very good reason to believe that you're in very good shape for our exam. Like it's not a trick. Our exam will not be identical, but it will be very similar. And in fact, as we get closer to our actual exam, if I start realizing, oh, like in this class, we never covered it, we did something differently, or if I'll keep looking at that old practice exam. And if I realize that certain things are slightly different in your class or something, I'll update the practice. Or if I find errors, I will continue to update the practice exam right to the end so that the most recent version that you ever get of it or the most up-to-date version that you ever see in Google Classroom of the practice exam will be the most accurate reflection I can possibly give you of what your exam is going to look like. In other words, in part, I'm trying to take the surprise element out of the exam situation. I'm not saying it's going to be a joke, and I'm not saying everybody's automatically guaranteed an A, not at all. But I am saying that some of the aspects that often make exams hard are not elements that I'm interested in. I'm not interested in you spending a lot of time trying to guess what I'm going to put on it or things like that. Okay, so you'll know. So use the practice exam, and I'm not trying to trick you, I promise. What I know from experience is physics is already tricky enough. Mother Nature is already wily in her ways. They are hard enough for us to understand. You don't need me to try to deliberately trick you. That doesn't mean there aren't going to be tricky things. Anyway, okay, so first of all, if all kind of typical questions like what's going to be on the exam or how the question's going to be phrased or this and that, your guide is the practice document. That's the single best way to study. Absolutely the best way to study is just live by the practice exam and try to do it. And anytime you don't know how to do something or you have to look then look up in your notes or in past videos or or Khan Academy or whatever resources you want to figure out how to do things in the practice exam. That's the way. Don't just start reading a book or something like that. Anyway, so okay, that's number one. See, I knew I was going to get you. Number two, as you might have noticed or as you might have read in the Google Classroom thing already, not only do you have a practice exam to guide. I'm sorry. One other thing about the practice exam. when possible, or if I have time, I'll even try. I will certainly. The other reason you want to look at it from here on in, like there's no new homework being assigned for a while. Your job is to go through that practice exam and see what you understand and what you don't, or what you can do and what you can't, and stuff like that. And you're welcome to bring questions to the next couple of class periods about that practice exam. Like mostly what we'll be focused on in class, the next two periods, I will already just be focused on stuff from the practice exam. I will be trying to finish this topic of material and get you ready for your exam. I'm not going to do. So you're allowed to bring questions. We don't do like a big formal review session or something like that, not in lecture, but you can definitely bring questions about the practice exam. And you'll also note, this is what I was going to say, you'll also note that if you go back through old videos from this class, like last semester or the semester before or whatever, I mean, poke around the old playlists, you will see that I do walkthroughs of problems from the practice exam, from their exams that are very, very similar. They're not always the same numbers. They're not always exactly the same problems, but they're very similar. And I mean, and it is not cheating. It's not cheating for you to go back and see me walk through solutions of those problems. And the fact that they're there is all the more reason that I won't feel like I have to walk through every single bit with you in live real time now, because they're all there. But I recommend, like, so in other words, you will not only, before you take your exam, you'll not only have a document that basically shows you what your exam is going to look like, but you can find the answers to it or solutions to it, online and stuff. And none of that is cheating. Now I'm going to go a step further. When you take your actual exam, take home, when it's posted Thursday, October 31st, and you have till Monday to do it, even then, and I know this is going to strike some of you as weird, but even then, the exam is an open universe experience. Even while you're actually taking it, you can look at stuff. You can look at old videos. You can look at your notes. You can look at old homeworks. You can look on the web. You can even look your friend in the face and sit there with your friend, your colleague, all your friends. You can sit together and talk about the exam while during the weekend. Not only can you, I would encourage it. So now this may strike many of you as very weird, or some of you might think, oh, this is a total joke then. This is a giveaway. Like, he's an idiot. Yaverbaum's an idiot. Like, is he crazy? Like, all right, guaranteed it. Well, let's be careful. What I'm telling you, well, I'm telling you two things. I'm telling you, on one hand, yes, a lot of the normal things that that we all get stressed about, I'm hoping that we won't get stressed about. Like, I'm trying to reduce certain contributing factors to anxiety. But I'm not trying to make this a joke. I think physics is hard. And I'm not saying that you're automatically guaranteed an A on this exam. Like, you do have to do this exam in order to do well. And sometimes people do badly on this exam. In fact, often a lot of people do badly on it. You have to be careful. What I'm saying is, I do take the notion of cheating very seriously. I do think cheating is bad. And people have been caught and I'm not trying to scare anybody. I'm just laying it on the line. There have been issues of cheating in the past in other physics classes and in my classes. And when they arise, I take them very seriously. I'll just put it that way. However, my notion of what constitutes cheating might be slightly different from some other people's. First of all, so there's two things that I think of as cheating. Okay. Number one, what I think of as cheating is when one person gives him or herself an advantage, an unfair advantage. When somebody gives themselves an advantage that other people don't have, particularly because the other people are honoring the community and this one person isn't. In other words, if I told all of you that you can't use the web, right? If I told all of you that it's a take-home exam, but you can't use the web, and most of you just agree, like, we're like, all right, I'm going to do the right thing. I'm going to follow the rules. I'm going to play fair. I'm going to be ethical, and I'm not going to use the web. But if one of you then said, forget it, I'm above the law, or I'm panicking, or whatever, and this doesn't apply to me, or I don't care that it's supposed to apply to me. My needs are more important than everybody else's. So they're all honoring the code and not using the web. I'm going to go use the web and I'm going to get the answers from the web that they don't have because, right? That's cheating, right? When one person takes advantage of other people's ethics and then like comes out ahead because they broke the rules that other people followed, that's cheating. And it's terrible. It basically says, I'm more important than you. Well, so my first point is, all right, let's get rid of all of that. I'm not, and obviously I've done this many, many times. I'm just explaining to you why I do it this way. Believe me, it works for my standards. I'm saying, oh, no, 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 let's get rid of that. Let's not like play games about this and let's not falsely tempt you. Like you can all use the web. You can all use your friend. Like everything that you normally consider cheating is not going to be considered cheating in this exam. Not only can you do it, but you should do it because I want you to learn physics. So I want you to help one another. I want my fantasy is that the way we do exams actually motivates people to make time to get together and make not just study groups, but like let's rock this exam group, like groups where people help each other and figure out the physics. Like that's actually makes me happy to visualize. So I want you guys doing all that. And in fact, I want people to know that if they don't do that, if you don't go on the web, or if you don't help each other, or you may be putting yourself at a disadvantage that I don't want you to do. So it's open universe. It is open universe. And let me add another thing to that. Please remember, in this class, and in Physics 204, there is no limit to how many A's I'm willing to write down on a final transcript. Like, I'm not saying that everybody always gets A's. And I am not saying that every semester, some people do fail. I'm not saying that to scare you. But I'm just saying nothing is a guarantee. But what is the case is that I don't care. I want you all to succeed. I want as many A's as possible, as long as they're legitimately earned. So you should not think that your ability to get an A is jeopardized by someone else's ability to get an A, right? Because once there's competition, then of course people don't help each other and stuff. That's not the nature of this. I mean, that has its place, but this is not that place. So I want you to help each other. I want you to explain the physics to each other and get into groups, et cetera, and use whatever other resources make more sense to you than I do, right? I want you to learn the physics. And I want you to realize that by helping each other, if one person is a little bit more confident of the material, it seems clearer to them than another person. I guarantee from long years of experience, I can tell you that if the more confident person is willing to sit down and talk through the material with the less confident person, they both benefit enormously. It is not charity. It's not philanthropy. Like, and the person who's teaching ends up learning things that they could not learn, but for trying to force themselves to explain it. And the person that's learning, like, certainly learns, right? So this is what I want, or this is what I'm encouraging. It is an open universe exam so that you have an even playing field, so no one has an unfair advantage, so that you cooperate and help each other learn the physics and all of that, okay? That's like, so that addresses my first. So don't think this is a gift or a joke or that you're all cheating. You're not cheating because it's not cheat anyway. But then the second issue, of it being an open universe take home exam, is that the flip side is in terms of what my expectations are and what you're turning in and what you're trying to do and how I'm grading it. The flip side is the other version of cheating that I do care about, the other that's much more personal and harder to legislate. What's also cheating, especially in physics, what's cheating is to write something down that you know in your heart you don't understand. That's cheating. That's a lie. If you write, especially in an exam context, if you write a bunch of stuff down, even if it's true, if you don't know what you just wrote down, if you don't know why it's true, or you don't understand it, or you just copied it from somewhere, I don't care about citation. I mean, all this physics is coming from somewhere. No one's claiming that you're or I am originally making up physics. So it's not a matter of quotes and citations and things like that, but it is a matter of, in the end of the day, what this exam is meant to test is your understanding of this material. So that means, yes, you should all help each other. And yes, you can be looking at whatever you want while you write this thing out. But at the end of the day, each one of you is writing out your own document and putting your name to it. And you are not being tested on whether you have the correct answers or not. Because the flip side of everything I just said before, the flip side of it being open universe and all of that is that I know it's open universe. I know that you have that all the answers are out there. Like some of them, I even give you the answers in videos, that I made. So I know you have the answers. So that's not the exam. The exam is you don't get an A just for putting down correct answers. That's not the exam. The exam is that you're showing me the derivations, the argument, the thought process, the 5-step method. You're showing me by the time you write down all your work that you fully understand how we get from a particular physics question to a final physics answer. Your exam is not a big quiz. It's not a Scantron thing. What it really is a presentation. You should think of your exam more as a paper or a presentation or a big document where you are demonstrating a physics thought process. You're demonstrating how fluent you have become in the language of physics. So it is possible to have a lot of wrong answers and still get a very good grade because what I'm grading on is the 5-step method. I'm looking for all the steps and really the intricate, authentically described steps of your reasoning. That's where I'm taking off or putting on points is the steps. So if you do all the steps really extensively and you give really ornate thought process that's really convincing and shows you know what's going on, even if there's computation errors or wrong answers, it's possible to get an incredibly high grade. But conversely, any exam, and this has happened in the past, is any exam where people are just like giving me the answers, that's not, even if they're all correct, that's not a high grade. That's not what you're looking for. I already know you have the answers. You're in your exam. So after you all help each other and stuff, then you go back to your private Idaho. I mean, give yourself time. After you discuss things and go on the web and research and understand stuff, now that you understand it, now you sit down and I highly recommend you make a rough draft of your exams just in the manner that you've been practicing for homework. All the homeworks are practice for this experience, like blank pieces of paper. I mean, you clean white sheets of paper where you make the question first, you make the question totally clear. You have a diagram and fact pattern. You say, this is what this is step 2 of what the question is. Then you do an extensive thought process of step 3 and step 4. You use different colors. You have annotations up in the margin, like you be you. The more you actually now get why the answers are correct, this is your opportunity to make a super clear, super thorough, super inviting, easy to read, easy to follow document that lays out all the physics understandings, right? So by the time you sit down and write it, so make a rough draft and then make a final copy and make the final copy as inviting, like think of it as a paper, not as a quiz. And think of that final paper as yours. Like, yes, someone might have held your hand through every explanation right up until the last minute that you wrote that thing. That is fine. Like, you may understand no physics right now still, but then in the next week, you're going to like get together with your buddies and figure it out. That's fine. But then once you sit down, you're showing that occurred and you're showing that it's now gone into your mind and you actually get this physics and you're writing out a presentation, a full self-sufficient document that's so clear and inviting that I don't have to look at anything else to follow it. I don't have to look at the original exam. I don't have to go back to I can just see what you're doing, what the question is, what the answers are, et cetera, et cetera. And again, the more colors you use or the more, and make it neat. Like it's a presentation. Like don't just scroll it out under time pressure. Make it so, because I have a lot of these to look at. And I'm telling you right now, a lot of them sometimes are very long. People, and I'm not trying to stress anybody out. I'm just trying to give you a clear picture. The good news is you have all the resources and all the help you want to do this, and you have time. And there's no time pressure, there's no webcams, none of that. That's the good news. The bad news or the real news is like, no, so therefore I'm holding you to a standard. This is your opportunity to present how you're thinking about physics, and that means how you are thinking about physics. The, like one thing I often say is just imagine that this were a class in Arabic or so, for example, like, and I'm not, so say it was a class in Arabic. I'm using that as an example because Arabic is a hard language that also has its own alphabet and its own symbols, right? Just like physics. I mean, it's like, so say it were a class in Arabic. If you had an exam that was take home where you had to write a full essay about what you did for your summer vacation or something, right? Yes, we both, and let's assume I knew Arabic, which I don't. Um, like, yes, you could go to the web and get a whole copy, a whole bunch. You could figure out the words for summer and wherever you went and house and this and that. And you could like copy all the symbols from the web and all this, and you could piece together from artificial intelligence, from chat GPT and stuff like that. Of course, you could piece together a whole thing that looked like Arabic and that described what you did for your summer vacation. But I think you and I know that if you honestly don't know Arabic at all, if you don't know Arabic and you don't know the symbols and you're just piecing it and faking it together from the web, but if I do, we both know that I could tell the difference. If I read your essay, I would know I would, even with ChatGPT. Let's be clear. Like you can fake a lot of things, but you can't fake fluency in a language. It's just what I'm asserting, right? I mean, or to a point, you can't. So I would know if you were trying to kid me into thinking that you could think and speak in Arabic if you literally could not. And honestly, just so you know, physics is the same way. What's cheating is if you get a bunch of equations from the web, even if they're correct equations, if you just write down equations that you get from the web or get from someone else and you don't know what they mean and you don't know how to use them or why, I am just telling you, it's obvious. It is totally obvious to anybody who does speak and think in physics. Okay. And in fact, not to make too much, it's really a lot of times what people do is they start putting down equations and just from the way they notate the equations, they're clearly notated from the web, not from the way we do in class. And that, again, that doesn't mean they're wrong. And it doesn't mean you're not allowed to get things from the web. But if after a point, all the notation you're using and stuff is different from it just becomes so evident that you put things together. So what I'm saying is there's two ways to cheat. One is to have an unfair advantage that nobody else has. Okay, that's not going to be the case here. The other way is to write things down that even though they are true, you don't understand them. That is cheating. And that's what you, and that's, and I'm not going to, and that, whether you call it cheating or not, that's what the exam is trying to just not allow, not what the exam is looking for is that you show your understanding. And it is evident when people write down things that they don't understand. Believe me, it's evident. So, okay. So, already enough about all that. We will say more about the material. Like I will, again, in the next couple of classes, I'll be addressing things from the practice exam. I will be guiding you more directly about how to do this exam and stuff like that. And I'm not trying to scare you right now, really. I'm just getting all worked up. But I am saying as you start moving toward the time period for this exam, think of it as a presentation, as a paper. Don't think of it as a quiz, and give yourself time. Like make sure there's time before it's due that you can sit down quietly and put all your thoughts together into a document that's going to be many, many pages. It is going to be many pages. And by that point, make sure you're doing it your way and translating it through your synapses. And then you put your name to it, and that's your exam. Okay. And lastly, and you do have to turn in it on time. Like I am loose about homeworks and all that kind of stuff. The exam has to be turned in by the beginning of class of Monday, 12:15 p.m. Monday, November 4th, right? And you have to come to class. That technically that period, November 4th, 12:15, technically that's our exam period. So like you will have already turned in and you can breathe out, but then you have to show up and sit in class. You do as part of the exam experience. Just because if you don't show up to class, then your classmates don't know whether you've turned it. Showing up to class is your way of signaling that you did your job and you turned the thing in on time. And if you don't show up to class, then your classmates think you're still sitting at home scrambling, finishing it, which is what people try to do often. And that's unfair to them. They shouldn't even have to wonder whether they did the right thing. And now they shouldn't have to sit there and wonder, wait, are they still doing their exam now? And is Yavrbaum, because Yavrbaum's such a pushover, is Yavrbaum going to let them get away with this? And should I have just done that? Like I cut my thing off like in the middle, like, and the answer is no. Like they're not. Like they will. Like there are consequences of doing that. So you've got to turn in the exam on time, 12:15, Monday the 4th, and show up to class, even if you like space out, just to show group solidarity. Okay, I'm not sorry, but if you follow what I'm saying, I mean, sorry, this is a rough day. Sorry. Um, the real message I'm trying to get across that I will do in a more soft way in the next couple of classes, if you do believe me and trust me, and you're willing to embrace this method of taking exams, if you trust that, if you don't view it as a joke, but you view it as a way of separating out unnecessary stress and just focusing on what's intrinsically stressful about physics, then it will work to all of your advantages. Then those of you who really feel like you are understanding the material, maybe even bored by it, those of you who, whenever you get to a part on the exam where you actually do feel like you understand it, you just go to town, go crazy. That's a time to show off. Like, again, use many different colors, make different pictures, make little cartoons, like go to town and take pride in your presentation and show me how clear it is that you really get it. It's really easy to do that when you do get the material. And by the way, you'll see that even though we both have the same answers, your exam is going to look totally different from what my board ever would look like, or what like once you get physics, it's like a language, like anything else. Everybody expresses themselves in their own personal way. So those of you who feel like you're understanding what's going on, this is an opportunity for you to really rock my world and really and produce something that you're proud of. Those of you who even at the end are still not feeling so secure or confident, which is fine, and there always are many of you, if you're feeling rocky about the physics, this is also an opportunity for you, because what you do is do the same thing I just said. If you don't feel that confident about things, be super honest and thorough. That's all the more reason you want to show as much thought process as possible. Okay. You too want to show different colors or different cartoons or this or that or thought bubbles or captions. Or you too, if you're not confident of things, the best idea is to be as honest and thorough about that. Like you write down the things you know, and then where you don't like things, like where equation, you literally write out things like, I still don't understand, or this is fuzzy, I'm not sure about this, but I think this leads to that. Here's something where I'm still having issues, and try to be as articulate and forthcoming and honest about your thought process, especially if you don't feel confident. Because again, what we're being graded on here is thought process. So it's an opportunity for people who really know to show that they really know. And it's an opportunity for people who don't know or don't feel they know to give me a lot more to work with, and a lot more room to give you points, and a lot more room to see how hard you're trying and how deeply you're thinking. Okay, so the flip side of everything sort of stressful that I said before is this type of exam, if you give it time and if you take it seriously, if you don't just think, oh, this is a joke, I'm just going to copy my friends. If you take it seriously, it's an opportunity to get an A for people who already feel A worthy, and for people who do not yet feel A worthy. That's the design. That's the idea. So please don't let me stress you out. Just take it seriously. Okay. I'm stressing myself out. All right. I'm going to move on. I'm going to totally shift gears now. And again, you could still raise questions about it on Monday and Wednesday and so forth, but now I'm just going to get back to physics. Can I just ask quickly, since I'm shifting gears? So I want to get to 2D kinematics, i.e. I want to give you a concept now in the next, oh my God. Oh, yeah. Sorry. In the next 35 minutes, I'm going to do one problem that is a practice problem. Like it underlies homework 7. It's like going on a lot in homework 7, and it underlies lab 3 and lab 4, but it's a fresh problem that I'm doing as an example right here to bring together a lot of things. And it's going to be a problem in adding two vectors together. That's what we're going to do here now. So since I'm going to take a breath and shift gears, can I just ask for a moment? Can I just see, I'm just switching the screen for a second. Can I just see a show of hands if, because I know that was a lot, what I just did. Can I just see an electronic show of hands if you're basically get the idea of the exam and if you're basically ready for me to now move? Okay, cool, cool. All right, thank you. You guys are a very responsive class. It means a lot. I really appreciate that. Okay, thank you. Awesome. All right, so, and you still can ask questions anytime. You can put in the chat or put in the text. But all right, great. Oh, Emmanuel. Oh, okay, okay. So, okay, shifting gears and switching the screen view again. Okay. We're now entering the land of two-dimensional kinematics, or you already did, like now in lecture, we're entering that land. You entered the land of two-dimensional kinematics the minute you did lab 3, and the minute you started considering the big old duck was a transition to this, but certainly the minute you started lab 3, the minute you did lab 4, and the minute you started homework 7, which we will go back to and do more concretely, but we're now starting to analyze motion in time and space in the space of a plane rather than just in the space of a line. Everything up until now has been motion within a line, which seems very oversimplified. Like, how's that? No, in the physical world, nothing exists just in a line. But the whole idea is that the physical world seems to be like three-dimensional in space. What we're trying to say in physics is we start with one dimension, not because we're trying to lie or oversimplify. We're saying Galileo's principle of relativity, form number 5, which I wrote at the beginning of the board like 2 days ago. I'm not writing it again here, but remember what the fifth form of Galileo's principle of relativity is look, every two-dimensional situation is really just two one-dimensional situations occurring at the same time, but independently of each other. That's the premise here. Like that's the principle. And so why we spent so many weeks on equations that only seem to apply to one dimension at a time is our theory, our way of looking at the world is if we understand this dimension, then all the rules for it work the same way as they do for this dimension. And anything that's happening in both dimensions, if we're careful and just separate and treat this dimension as happening by itself while this one's happening, we shouldn't really need any more equations or laws or anything like that. And then therefore we can then extend it to 3 dimensions, which we do next. We could deal with the world as long as we deal with it one dimension at a time. Okay, so that's the concept. Now, the mechanical or the mathematical or computational, one major computational technique that we will deploy throughout two-dimensional motions is this technique of adding vectors. What I'm going to teach you today, in a way today is I'm teaching you addition. It's almost like we're going back to 2nd grade and we're learning how to do 2 + 2 and get 4, okay? But we're learning how to do addition now. We're going to learn a technique for doing addition where we're not just adding raw numbers together. You already know how to do that. You know how to add the number 2 to the number 3 and get the number 5. What I want to show you today is one method for adding vectors together, i.e. adding quantities together that not only have a size, but have a particular direction. And more specifically, I want to show you how to add together quantities that have a size and a direction within two-dimensional space. In other words, a direction that's a little bit more complicated than just plus or minus or something like that. So I want to show you how you add together two-dimensional directional quantities. That's what we're going to do. So we're going to show you how to add vectors. Before I go any further, I got to say, what do I mean by a vector exactly? Okay. A vector is a graphical or pictorial representation of a vector quantity. Like in this, so let's remember, in this class already, we make this distinction between quantities. Some quantities are just scalar quantities like distance or average speed. We call those scalar quantities because they just have size. But there's other quantities in physics that are called vector quantities. A vector quantity has not only size, but also direction, such as displacement or average velocity, right? Or acceleration for that matter. Now, so a vector quantity is a quantity that has magnitude and direction. From here on in, now that we're entering 2 dimensions, direction is it's a subtle enough idea that we want to keep track of it in a way that's helpful and that we can picture. So we use from now on arrows. We use an arrow and we call it a vector. So a vector is an arrow that is used to represent a vector quantity. I say represent. I don't just mean loosely remind us of. I mean represent in the same way that a graph, a regular everyday graph, represents a relationship in the world. And if you draw your graph to scale, if you're careful about it, or you use a computer to make a scatter plot, like graphs are not just like rough approximations. Graphs are representational tools, right? Like once you draw a graph seriously, then you can take the points on it so seriously that you can make measurements. Like you do a trend line through the points and then measure the slope of that trend line. And by measuring the slope, you believe you've actually learned something about the rate of change of an actual relationship in the world. In other words, graphs are actual computational tools, right? If they're drawn seriously enough or by a computer, then they literally become like little calculators on their own. Same thing with these arrows. A vector is just an arrow. I mean, I'm not trying to a vector is just an arrow, but it's an arrow that if it's drawn to scale, if we take the drawing of it seriously, then when we put a bunch of arrows together on a piece of paper, just by looking at the drawing, just by making measurements from that drawing, we will have in effect performed a computation or a calculation. Like these arrow pictures are not just rough pictures. They are computational tools. And again, that's what I sort of want to show you today. Now, honestly, that's what you were getting exposed to when you did lab 3. We didn't explain any of this before lab 3. That's the way, because it's a lab. Like you're experimenting around and playing around. But in lab 3, when you like just drew a bunch of arrows to get off of Survivor Island or whatever it's called, we were trying to expose you to the idea that if you take these arrows seriously, you can eventually use the arrows to see things numerically that you can't see in your head. So a vector is an arrow whose length represents the magnitude of some vector quantity and whose tip to tail orientation represents the direction of some vector quantity. To be more specific, we're now in 2 dimensions. So when I say direction now, I mean something more than just plus or minus. Plus or minus, forward or backward, north or south, plus or minus was a designation that worked for direction as long as we were only within 1 degree of freedom, 1 axis. Now we're moving within 2 axes. So each axis itself has to be distinguished. A plus direction has to be distinguished from a minus direction. Each axis independently has its own plus and its own minus. But then once you move within the plane defined by those 2 axes, then you end up moving in directions that are best captured overall by angles and points of the compass. In a physics, so for example, here's a vector right here, this yellow arrow. This yellow arrow on the page is an example of a displacement vector. It's an arrow that represents 15 meters of distance through space in a direction of what I will from here on call 30 degrees northeast, like assuming the blue thing assuming that I'm calling to the right on the page east and positive, so I made a little legend, I made a decision, I made a coordinate system in blue, Galileo, Galileo, Galileo. And then assuming that coordinate system, my yellow arrow is an arrow that's pointing that represents someone, for example, who walked 15 meters, 15 meters at 30 degrees to the northeast. Let me make a couple comments about that. Say it had gone like this. Say it had gone the other way. Maybe in a math class, you might say that going the other way is like an angle of 150 degrees or something like that. And that's okay. I'm not saying that's wrong. But in physics, we're interested in like space and time of the world. So the way we do directions in two-dimensional space in physics, the way we tend to is we always use acute angles. Like you might want to write this in. I mean, I'm saying our angles, I'm saying direction always requires an angle. And furthermore, it requires points of the compass, because in physics, the way we do angles is we always do an acute angle. We'll never say like 150 degrees. We'll say something like 30 degrees northeast, or if the thing went this way, we would say something like 30 degrees northwest or 40 degrees southwest or something like that. We always use points of the compass and an acute angle to designate direction. So you want to get used to that. And it might help to realize that when I say something like northeast or southwest, that's really an abbreviation. What it says up here to the side that you can barely read, N-E, northeast. What that really is an abbreviation for is north of east. So northeast means, imagine like this dotted yellow reference line. Imagine a reference line pointing to the east. But what we're saying is we opened up an angle 30 degrees north of that eastern reference line. I'm not saying east is always the reference. That's why there's a such thing as like northwest. If you say northwest, what you're saying is imagine a western reference line and open the angle that many degrees to the north of it, okay? So every direction is an angle, every direction is an acute angle and points of the compass. So this is an example of a displacement vector, of one displacement vector. I want to say one more thing that I would highly recommend you putting in notes before I move on. This is an example of a displacement vector. In a minute, I'm going to add it to another displacement vector to give you an example of how to add displacement vectors. But what I really need to emphasize here, that's really important for the exam and for if you're thinking, okay, this is fine, but this has nothing to do with all that stuff in homework 7 or nothing to do with what was going on in lab 4. Like I hear you. I could see why you might think that. Because what I'm saying is right now, I'm focusing on display. This is an example of a displacement vector. But as I say, you may want to put in your notes, that yellow arrow could have looked just like it. And it could have said instead 15 meters per second. It could have said 15 meters per second, in which case it would be a velocity vector. Like any quantity that is a vector quantity can be represented by an arrow whose length represents the magnitude of the vector quantity. So let me back up further. Say like, so this one's 15 meters, right? You'll see in a minute. If I wanted to depict 5 meters of displacement, I would draw a separate arrow that would be like a third as long as this one, as you can imagine, right? Like we try our best to keep to some scale. Like in principle, if you're really being careful, you would literally use a ruler and a compass to draw every one of these arrows, or a computer, right? And then they would really be effective as computation tools. But I'm saying, even if you're being somewhat rough about it, this arrow is 15 meters. That means, this arrow is that long. It's representing a quantity of 15 meters. If I wanted to depict 5 meters, I would draw an arrow a third as long. I'm sure you understand that. I believe you. But I also want to say, and so that arrow represents literally 15 meters of displacement from one initial position to a final position somewhere in space. But I could have drawn an arrow just like that and labeled it 15 meters per second. And then, and if I wanted to make it slower, like 5 meters per second, I'd make it a shorter arrow. But then the arrow would be representing a velocity. It would not be it would have length on the paper, but please remember, it's a representation. So a shorter velocity arrow would be a shorter velocity arrow, but it'd be shorter so as to represent a smaller magnitude of velocity, i.e. a 5 meters per second arrow would represent someone at some point in space and time moving very slowly. So I don't want to get bogged down in this, or similarly, you could have an arrow to represent 9.8 meters per second squared of acceleration. The arrow can represent any kind of vector quantity, and the arrow looks like a length on the piece of paper, but it's only representing a length in space if it happens to be a displacement arrow, a displacement vector. If it's a velocity vector, it's representing motion at a moment in space, etc. So just bear in mind, so everything I'm about to show you what happens when you add two displacement vectors together, or how to do it and how to get an answer. I want you to realize or somehow notate that I'm focusing on displacement here today because that's how you originally got introduced to vectors in Lab 3, and because displacements are the easiest things to picture. Whatever space is depicted on a piece of paper is actually representing space in real life. But any method I show you for putting together two displacement vectors today is the same method you will and should use if ever you're putting together two velocity vectors or two acceleration vectors or two force vectors or two electrostatic field vectors, like in Physics 204. Specifically, you'll see, or you've already seen in the homeworks and in the exam, there's places where you have to deal with velocities and adding them together in 2 dimensions. I want you to be aware as of now that the method that you put together velocity vectors is the same method that you put together displacement vectors. It's easier to see first with displacement vectors, so that's what I'm going to do right now. But just understand, this is a universal method of adding vectors. So it says, vectors of all kinds can get added together. And the way we add them together is the same way. And so I'm going to show you through displacement vectors now. We add displacement vectors according to this GPR, this principle I keep saying. We're going to add displacement vectors by recognizing that every 2-dimensional quantity is really two 1-dimensional quantities occurring simultaneously yet independently. Like, that's the concept, but as many of you frequently asked, okay, but how do these abstract concepts relate to concrete problem solving? Okay, how that relates is I'm going to now show you what is called the component method for adding vectors. We're going to add vectors by resolving them into individual components, and that is the mathematical way of saying, so we're going to take 2-dimensional vectors and we're going to treat each one as actually being two 1-dimensional things happening. We're going to resolve it into its two 1-dimensional components, add those components up, and get an answer that way. And that's what I'm going to show you right now. So this is the component method of adding vectors, adding two vectors. So example, so let's say we have two vectors, vector 1 and vector 2. They're both displacement vectors. And they're they're representing some journey, some little journey that I just took. Like, say, so here's the example. Say first, vector 1, I walk 15, I started some position, call it A. Sorry, I started some position in space called A, and I end up at some other position, call it B. But this is how I do it. I start at A and I walk 15 meters at 30 degrees northeast. In other words, the other vector that I already had drawn 2 pages ago. I do that vector first. I displace myself according to that vector first. But then let's say when I get to the 15-meter mark away from the original, now I rotate my body and I walk 5 meters, but in a different direction, at a direction of 60 degrees southeast, let's say. So in space, I've walked like that. And the ultimate question is, the ultimate question is, what is my total displacement for this entire journey? i.e., how far, remember, displacement is a vector quantity. It has magnitude and direction. So what I'm asking for this is, at the end of the day, at the end of performing vector 1 and then vector 2, how far away and in what exact direction is point B from point A? That's what I'm asking here. I'm asking, if I do that and then that, How far away am I at the end of the day? And in what direction did I travel at the end of the day as a result of these two displacements being added together, right? So that's what I'm going to try to figure out. What is my total displacement? What's the magnitude? And what's the exact angle direction for this addition of displacement vector problem? And we have 15 minutes to do it, which will be fine. So we're now going to perform a computation. Let me start by saying you can't do this in your head. If you're understanding what I'm saying, basically the answer is not 20. Like, I can't do this in my head. Like, the actual answer to this problem is not a round number. The actual answer to the distance, to the magnitude of displacement is not a round number. And the actual answer to the final direction, the final angle, is not a round number. So there's something that actually has to be done here. And that's what I'm going to show you now. First of all, like I just said, like the answer is not 20. Like yes, we're adding these two vectors, but we're not adding numbers, we're adding vectors. We're trying to figure out the overall accumulated effect in space of having done this and then done that. Well, if I just added 15 to 5 and got 20, what that would be is the total distance. Sure, if I walk 15 and then I walk 5, my total distance that I walked is 20 meters, but that is not what I'm asking. I'm asking what's the total displacement. In other words, if I want to know the total displacement, I want to add these two displacement vectors. And the first thing I'm going to teach you right now that I want you to emphasize in your notes, whenever you add two vectors, not just two numbers, but when you add two vectors, the way to picture it or represent it is you place the two vectors tip to tail. When you place two vectors tip to tail, always, whatever the vectors mean, you are adding them. So these two vectors, and it makes sense, right? Like I walked this way, I finished that journey, and then from where I finished that journey, I started a new journey. So if I place the two vectors tip to tail, what I'm saying is the dotted yellow line that completes the triangle, that would be the total displacement. Like the size and the direction of that yellow dotted line is what I'm looking for to solve for in this problem. If I literally drew these vectors like perfectly to scale, used a ruler and a protractor or a computer and really drew them out to scale, then what I'm telling you is and this again is like lab 3, if I measured out the dotted yellow line, the length of it would be the answer I'm looking for. And if I looked at exactly what angle it makes with the imaginary Eastern reference line, if I measured that angle with a protractor, that would be the answer to the direction. So number one, partly what I'm saying is vectors are real computational tools. If you draw them super accurately, the drawings themselves will give you answers if you do measurements. But what I want to show you here is how to get the answer without measurement. Like, how can we analyze how can we get the final answer? So that's what I'm going to show you within the next 12 minutes. Just one last thing, though. Just notice, if you look at the diagram, I hope you can see the diagram. The diagram is like predicting, and it's not perfectly drawn to scale, but it's somewhat drawn to scale. According to the diagram, it's saying that my final displacement, the answer that I should get at the end of the day, is definitely going to be smaller than 20. I mean, it's a more direct route than going off on that turn thing. It's less than 20. But I think you can also tell it's greater than 5 and it's greater than 15, right? I mean, it completes the triangle. It's greater than either of the two sides, but it's not greater than the sum of the two, but it's not equal to the sum of the two sides. And furthermore, if you look at that picture, it's probably not that much greater than 15, right? In other words, I walked 15 a certain way, and then I kind of backtracked, then I kept going easterly. But instead of continuing to go north, I'm now going south. So I sort of backtracked myself on one axis while I advanced on the other axis. So I didn't end up gaining a heck of a lot from that last leg of the triangle. Like, I hope you can see that at the end of the day, how far I walked is probably a little bit greater than 15, but not much greater than 15 meters. And I hope you can also see from that, like as a checkpoint or as a prediction, that the angle I ended up going, well, I ended up going probably somewhat northeast because I was always going east, right? I was going east and then more east. I was going a lot north at the beginning, and then it went a little bit south at the end. So I'm going less northernly by the end of the day than I originally was. In other words, it's showing in the picture that at the end of the day, presumably I did walk somewhat northeast, but not as steeply as 30 degrees northeast. Some angle smaller than 30 degrees, presumably. I mean, I don't know. So that's what this is predicting. And at the end, when I get my answers, I should check back that my answers make sense with this original predictive tip to tail depiction. But how do I get the answers? How do I actually analyze the numbers? This is how. We embrace the Galileo idea. We zoom in on each, and this is, again, the method I'm telling you now. You might have done other, you might see other things. You might be thinking like law of cosines or law of sines or all these other things, that each of which is very smart and sometimes works. But what I'm giving you now is a method that always works, whether it's 2 vectors or 3 vectors or 4 vectors, whether it's displacement or velocities or accelerations. Like, so trust me, even if you have other ways, they might have gotten you a right answer. But I want you to know this way, universally, this is called component method. I'm going to zoom in on each vector individually and resolve it into its individual components. That is, I'm going to zoom in on that first vector, 15 meters, 30 degrees northeast. And I'm going to say, you know what? When you go 15 meters to the northeast, what you're really doing is you're going somewhat east, while at the same time, but independently, you're going somewhat north. Right? I mean, anybody who lives in Manhattan or anybody who goes to school in Manhattan understands this. If you want to get from here to there, you not only can, but sometimes you have to get it by a series of theirs and theirs. You know what I'm saying? So I'm saying to go 15 meters northeast, what I want to do is back up and say that vector itself could be regarded as the tip to tail sum of 2 smaller vectors. To go northeast, I actually went somewhat east and then I went somewhat north, only not then in time. Then in my mind, like I went somewhat east, plus I went somewhat north, and that sum together made northeast. The only question is, how much east did I go and how much north did I go? Well, that's answered by SOHCAHTOA every single time. It's SOHCAHTOA, right? And so I'm going to say it once, but then I'm always just going to cut to the chase with these. SOHCAHTOA says, for example, if you're looking, it says, for example, the cosine of that angle equals the adjacent. Let me back up. I'm sorry. Why am I using SOHCAHTOA? Because this is necessarily a right triangle. One thing I want to make very clear. This is a right triangle, definitely, by definition, because I just took my arbitrary random northeast thing and I broke it up into a north pointing leg and an east pointing leg. I'm necessarily looking at it as a sum of 2 perpendicular axes, right? I am not saying that this thing is a right triangle. So these are where you have to be very careful. This is a picture that depicts the whole situation. A lot of people want to like do law of cosines or something on that picture. Sometimes that works, but I'm discouraging it. Or some people like to do SOHCAHTOA on that picture, but they can't. That's not a right triangle. That is not, the original situation is not necessarily a right triangle. But the method I'm teaching you says, take each individual vector and deliberately turn it into its own right triangle. So now you can believe and know for a fact that SOHCAHTOA and Pythagorean theorem and all that stuff will definitely apply. We're taking each 2-dimensional situation and breaking it up into 2 1-dimensional situations. So I say the cosine of the angle is necessarily adjacent over hypotenuse, for example. So if I'm looking for the adjacent side, multiply both sides by hypotenuse, the adjacent side is necessarily hypotenuse times cosine. And I'm going to do this every single time from now on. I'm not going to, like always in my mind, the adjacent side of a triangle is the cosine times the hypotenuse. And the opposite side of the triangle is always the hypotenuse times the sine. So what does that mean? It means that the length of the east, it means that when I went 15 meters at 30 degrees northeast, what I was really doing was the equivalent of going 12.9 meters to the east while going 7.5 meters to the north. Again, this is really what you were seeing in lab 3 when you realize, like, oh, you could take a bunch of vectors that had the same, that north can't, whatever. This is what you were seeing in lab 3. So my first vector, all I just did was break it up. I haven't added anything. I just resolved it into its individual one-dimensional components. And then I do the same thing for the next vector. The next vector went 5 meters at 60 degrees southeast. So I say, okay, that's really like going 2.5 meters to the east, SOHCAHTOA again. And it's like going 4.33 meters to the south. That's like in other words, 2.5 plus 4.33 in vector addition, 2.5 plus 4.33 equals 5. It doesn't, right? As long as the directions are the way I just depicted. If that didn't make sense, you just ignore it. But now, what do I do with all these numbers? What's the point? Where does the addition come in? I make an XY chart. I say to myself, okay, the X world is the X world is happening independently of the Y world. So in the X world, if I just look back at, okay, first I walked 12.9 meters to the east, then I walked 2.5 meters to the east. So I just tally those up in the X column. I got a total of 15.4 meters to the east, right? I'm treating them independently. Again, you can't just add up vector hypotenuses, but you can add up numbers in the same dimension because each dimension is its own world of physics. In the y-axis, I first went 7.5 meters north, but then I went 4.33 meters south. So I put a negative sign on that because we originally said, like, right on that axis, anything going south is negative. So I put a negative sign on that, and then I'm just adding up. I'm individually adding up. So I'm saying at the end of the day, I walked 12.9 and then I walked 2.5. So I walked a total of 15.4 east. And while that was happening, I was going 7.5 north, but then I walked 4.33 south. So that added up and I did a total of 3.17 north. So what does that mean? At the end of the day, I can make one big final right triangle. I could say at the end of the day, what I really did was go a total of 15.4 in the east, a total of 3.17 to the north. And that is, again, a right triangle necessarily. So the answer I'm looking for is the length and direction of this dotted yellow line, just like the original dotted yellow line that I drew in my original picture. The length of this dotted line, the magnitude of the displacement, I get from Pythagorean theorem, right? I'm going a little fast now. Obviously, there's 2 minutes, but I think you know Pythagorean theorem. I'm saying that this side is the square root of the squares, which works out to be approximately 15.7 meters, like we predicted, a little bit more than 15. Like not 20, a little bit more than 15. And similarly, the angle, the direction I went, how do we get that? SOHCAHTOA. Tangent of angle equals opposite over adjacent. Therefore, we don't want the tangent of the angle. We have the opposite over the adjacent. We want the angle itself. So we do inverse tan or arctan or tan to the -1 on your calculator. All same words for the same thing. I mean, all different words for the same thing. So the angle is the arctangent of the opposite 3.17 over the 15.4. And on your calculator that you get, that if you're in degree mode, you'd get approximately 11.6 degrees northeast. How can I tell it's northeast? Because look at my picture. It's north of east. So we have 1 minute. Number one, I'm saying this is my answer to the problem. At the end of the day, the total displacement is you ended up walking approximately 15.7. I ended up walking 15.7 meters away from my original position, and I walked away from it in a direction of approximately 11.6 degrees northeast. For it to be a final answer, it has to have magnitude, it has to have direction, direction has to have an angle and points of the compass. So this is my final answer, and if you're understanding what I'm doing, I'm saying those final numbers, those two numbers that I got, they're describing the dotted yellow line in this picture, which is literally the same sorry, whoop, as this dotted line in this picture. Like they are two different pictures of the same line. This dotted yellow line that I sketched originally predicted it would be a somewhat longer than 15 and somewhat less than 30 degrees. That is what I did at the end of the day. But I understood it by saying, oh, at the end of the day, what I really did was go like that and like that. And so I ended up with 15.7 meters, 11.6 degrees northeast. That's how you add any kind of vectors. Even if those were velocity vectors, they would mean something different, but we would add them together by the same method. And if it was 3 or more vectors, we just keep adding and adding by the same method. So that's it. I will hang out for a minute or two for questions if you want, whatever, but that's it. You've been very patient. Have a great weekend. I'm turning off the recording, but thank you for your patience.